The Carnot generator cycle represents the thermodynamic cycle that has the highest efficiency in order to transfer heat from a cold source and to a hot source using a mechanical work. It is best represented in a TS diagram, T like temperature and small s like specific entropy. So in such a diagram we can already plot the cold source and hot source temperature. So that would be the cold source temperature, and that would be the hot source temperature, T hot. The Carnot generator cycle is a thermodynamic cycle that will show 4 successive thermodynamic transformations in a fluid, and 2 of them have a constant entropy and 2 of them have a constant temperature. For this reason, we can also plot 2 specific entropies that would be characteristics to a given Carnot cycle. So I will write this specific entropy S1 and S2. So as it is a cycle, the state of the fluid is the same after each cycle, so we can choose where we want to start to describe it. I suggest that we start with a specific state of the fluid at low temperature and high specific entropy. So I will write point A at this location. So the first transformation we have in the Carnot cycle is an adiabatic reversible compression. So this compression will give place to a rise of temperature, and the specific entropy will remain constant, because if it's reversible there's no entropy creation, and if it's adiabatic there's no entropy transfer, so the specific entropy of the system remains constant. So that would be a Niso entropy transformation up to a point B. And this transformation is adiabatic, so there's no heat exchange. However, in order to do the compression there must be a work transfer, so there's a work transfer that will be given from that would be given to the system in order to do the transformation. So I can show this way with an inwards arrow showing the work that is received by the fluid. Second step is an isothermal reversible heat transfer. So here the working fluid will give heat to the hot source, but this transformation is reversible, so at all points the fluid will be at equilibrium with the hot source, that is at the same temperature. So this transformation will go from B to lower specific entropy point, but still at the same temperature, point C, at this location. So during this transformation there is obviously a heat transfer. The fluid is giving heat, so giving entropy to the hot source. That's why its entropy is decreasing, even though it's a reversible transformation. So in that case you have this kind of heat exchange from the fluid to the hot source, Q, B, C. During this transformation it is also possible for the fluid to exchange work because usually when we have a heat transfer, there's also temperature variations, and in order to remain isothermal during this reversible heat transfer, they can be also a joint work exchange. So I can write it this way because it would probably be this way and work from B to C. Third transformation is symmetrical to the first one. It's again an adiabatic reversible transformation, but this time from the hot temperature source to the cold temperature source. So in that case, it would correspond to an expansion of the fluid. And once again, if it is adiabatic and reversible, it is also at constant specific entropy up to point D, that is at the cold temperature source. And during this transformation, it's reversible, so there's no heat transfer, but there's a work exchange, and because it's an expansion, this time it's the fluid that is giving a work from C to D. And for transformation, last one is the symmetrical of the second one, but this time the isothermal reversible heat transfer is between the working fluid and the cold source. So in that case, the fluid will receive some heat from the cold source, and so from D to A, there's the isothermal heat transfer. Because the fluid is receiving heat, it is also receiving entropy, so its specific entropy is increasing. So that's QdA, the heat exchange with the cold source. And in order to remain isothermal, depending on the fluid, it may be necessary to have simultaneous work exchange, still reversible, and in that case it would be an expansion of the fluid, work from D to A. So that's the definition of the Carnot generator cycle, and that's the cycle with the highest efficiency as a generator. So the generator may have two use. The purpose of the machine can be either to remove heat from the cold source, so this heat transfer QdA, or the other purpose of the machine could be to give heat to the hot source, so this heat transfer QBC. And what we usually need to pay to make it work is the work that is provided to the working fluid for the cycle, so the sum of all the work of the different transformations. And because it is a cycle, the work of the cycle is identical to the technical work of the cycle. So from an energetic point of view, we can write easily the specific energy exchange during the different transformations. So for the energetic analysis, we can write the heat exchange with, for example, first the hot source. In that case, it's QBC, and here it's quite easy because we have a reversible heat transfer, and if it's a reversible heat transfer, all the entropy variation comes from the entropy transfer due to heat transfer. There's no entropy creation because it's reversible. So in that case, we can do the integration of TdS, but because the temperature is constant, it's an isothermal heat transfer, this is equal to the temperature at which the transformation is taking place, so T hot, multiplied by the variation of specific entropy, so S1 minus S2. And as S1 is lower than S2, this is a negative heat transfer, and this is as expected, because during this transformation, from the point of view of the working fluid, it will lose heat because it will give heat to the hot source. Similarly, we can write the heat exchange with the cold source. In that case, it's Q dA with the cold source, and similarly, because it's a reversible isothermal heat transfer, it's equal to the temperature at which this heat transfer is taking place, multiplied by the variation of the specific entropy S2 minus S1, and this time this heat transfer is positive from the point of view of the working fluid, because this fluid is receiving heat from the cold source. Then, concerning the work of the cycle, this is quite easy to calculate. So first, the work of the cycle is equal to the technical work of the cycle, and this is due to the fact that it is a cycle, so the state of the fluid is the same after one cycle. And according to the first principle of thermodynamics, for a whole cycle, the work exchange plus the heat exchange is equal to the variation of the specific internal energy, and this variation is zero because it's a cycle. So in that case, the work exchange of the cycle is just the reciprocal of the heat exchange during the whole cycle, so it corresponds to minus QBC minus QdA, and this can be written simply as a function of the temperatures and specific entropy, so it's T hot minus T cold times the variation of specific entropy S2 minus S1. Now that we know the work exchange, so the work that we need to provide to make it work, and also the heat exchange, we can write the efficiency of the whole cycle. And so the efficiency is always defined the same way. It's an economic parameter. It's the ratio between the absolute value of the useful energy or power divided by the absolute value of the energy of the power that we need to pay. So the efficiency definition depends on the purpose of the machine, and as I told just before, there are two ways this machine can be used. If the purpose is to heat up the hot source, so in that case it's what we call the heat pump, the efficiency is usually called COP, or coefficient of performance, and in that case the useful energy would be QBC, and what we need to pay is always the work of the cycle. And so concerning the Carnot COP, it can be written directly as a function of the temperatures, because the specific entropies are the same at the upper and lower part of this ratio, and in that case that would be the ratio of the hot source temperature divided by the difference of temperature between the sources. The other efficiency would be the cooling efficiency, and the cooling efficiency is sometimes written with this Greek letter, and in that case the useful energy will be the heat exchange with the cold source, so QdA. And what we need to provide to make it work, or to pay, is still the work of the cycle. And the Carnot efficiency can be once again expressed only as a function of the source's temperatures, and that would be the ratio between the cold source temperature divided by the difference of temperature between the sources. It can be noted that these efficiencies are not the ratio between a heat transfer and the maximum heat transfer that could be done. It's defined another way. For this reason, the efficiency may have a value higher than 1, and has often a value higher than 1. In the case of the COP of Carnot, it has to be higher than 1. And so that's different from other efficiency that may be defined for other systems, and the reason is that some energy exchanges are considered as neutral.